The space industry has long been a proponent of open processor architectures, relying on them for missions that explore the depths of our solar system. To learn how RISC-V is being adopted, I spoke to Sandi, Habinc, General Manager at Frontgrade Gaisler, to find out more. I started by asking for some background on the company and its microprocessor technology that's deployed in harsh environments such as space.
So Frontgrade Gaisler is a company was established back in 2001. We're a world leader in providing processor for harsh environments like space. We've been focusing on the microprocessors, rad-hard microprocessors for various missions. The company is also part of Frontgrade Technologies, which is a wider company in the US, where we have anything from power management solutions to standard products in terms of microelectronics to antenna, RF amplifiers, electromechanics. So it's a quite broad portfolio. But we, as Gaisler, we focus on the microprocessors. So if you look at Gaisler in Gothenburg, it is we range from IP cores, and that includes processors and any peripherals you can imagine used in the space domain, towards components where we offer ready-made solutions which are rad hard specifically for space, to development boards, to software tools such as debuggers, simulators, as well as the basics in terms of operating systems, board support packages for the processor. So it's a whole portfolio based on a processor and at the center.
So who are your customers and what are their key requirements when engaging with you?
So our customers, they range from governmental agencies like Space Agency, European Space Agency, NASA, to prime integrators, both in US and in Europe, all the way down to equipment manufacturers, as well as institutes who do instruments for spacecraft. And also managers of, let's say, large constellations. So it's the whole broad portfolio. So it ranges anything from let's say, the full spacecraft focus to a specific instrument. Well, number one is always radiation and reliability for space specifically. That's sort of one of the key things. In space, obviously, the electronics will be exposed to the harsh environment, from radiation to temperature shift, etc. So that's one of the things that comes up. The other one is the high performance of the computing they need to do the right thing in the right environment at the right sort of at right power consumption, temperature environment, etc. Low power, obviously very important for deep space missions, for example, where they don't have enough energy from the sun, etc., to run the instruments. We see also key aspect are definitely that they are tested, that the components are reliable. I mean that we do expose our components to harsh qualification processes, etc. So those are the main requirements.
What types of space applications are your customers tackling then?
There's a wide range of space applications that our components are being used and put to use in customers' applications. So it could be anything from probes going deep space or rovers landing on Mars. Quite recently, there's a lot of activities around lunar landers and lunar missions. We look at constellations, major constellations. We look at classical Earth observation, telecommunication, navigation type of application. So it's actually everywhere you can imagine that there is a need for electronics in space. You will find our products on that.
Talking about the IP libraries you provide, are your customers building their own silicon, or do they primarily integrate your IP into an FPGA, or are both options possible?
I think the beauty of our business model is that actually we offer all of that. It's all the way from the IP. So you have customers taking the IP, they put their either in an FPGA or into an ASIC. Both occur. Of course, there are many more doing FPGAs than ASICs right now. But also have customers that go straight for the component or a board level solution. So we cater to all levels of engagement from the customers. The investments into FPGAs are lower than, for example, into an ASIC, obviously, but it's perhaps sometimes even easier just to take a ready-made component that solves your problem.
So what is it about your RISC-V IP that makes it suitable for space compared to alternative solutions that are on the market?
So the way we've developed all our IP, and this is based again on our experience. I mean, 20 plus years in this business doing processors for space. It is the fault tolerance and the how we apply fault tolerance and what it actually solves for the customers. So some of the key elements that we have is the handling of detection. Obviously, everybody does that, but it's also the correction of these errors. To do that in a in a way that it doesn't disturb the software, but also that it's done timely, such that it doesn't disturb, let's say, the critical execution time slots that we have, for example, on motor control, etc. So it's the combination of these three things that we do. We do very well, and that's why customers choose our products.
Why is RISC-V attractive for space customers? Aren't there alternative processor architectures?
Yeah, to explain that, we have to go back a bit and see how it was in the 1990s. There were a lot of proprietary solutions in the marketplace, and it was very difficult actually for European companies to find devices sometimes for space. And a big decision was made back in the 90s to go for the Spark architecture, which was an open standard. It's the difference between open standards and open source, but it was an open standard such that anyone could actually make their own implementation. And this made it possible for multiple implementations adhering to the same standard, and also opening up the possibility for multiple sources of technology at the same time. So that Spark has been extremely successful over the years, where you can find a Spark or a Leon implementation of Spark on any spacecraft in the solar system right now. And RISC-V has the same properties. It's a open standard. It's not open source that's important, but actually an open standard that anyone can implement that. And by having the same standard being used in the US as well as in Europe, and even worldwide, it will strengthen the interoperability and the investments in software, etc. But also second sourcing, because sometimes you need more than one source providing a service for space. And also it fosters a very good competition. I think it's a good thing that we are selecting the same basics and then compete around that. I think that's a very successful way forward.
So Sandi, has your RISC-V processor been adopted in any EU projects?
Yes, actually in several ones. We have the RISC, Selene, Isolde. There are three different activities. The first one, the RISC, is specifically towards space, where we collaborated with Thales Group, for example, on developing a platform for hardware and software, which could form the basis for future space computer systems. In Isolde, we just recently started. We take that concept and go a step further, taking it to higher TRL, the same type of systems, and continue developing that. And the results from these activities are also being reused in European Space Agency activities, where we are developing the next generation of RISC-V processors for space.
And one final question. I noticed you have some FPGA development boards available. What sort of tools, both hardware and software, do you offer that help with IP selection and the subsequent development process?
So the question can be answered from two ways. One is from a software perspective and one from a hardware perspective. The important thing here is we're in the business of space computing, or in computing, and it's very important to address that from software side. So if we look at enabling customers to select our technology or developing with that, we do provide, in addition to FPGA boards, as you mentioned, also evaluation boards for those who want to go directly to the components. But in addition to that, we have debuggers, simulators. So for example, the Frontgrade Gaisler GRMON3 debugger, it's been specifically developed for the early generation of the Leons, but now we're also moving that into our RISC-V solution, adding features beyond the normal debuggers you would find in the market. And the simulated TSIM3, we go for cycle accurate simulations of the processor, enabling trade-offs on timing critical applications, etc., and already doing profiling of that. So that can actually help you with selecting or working with the technology even before there is a tape out or there is some hardware available. But then looking at it from the hardware perspective, with these FPGA boards that we offer, but also the FPGA boards, from other FPGA vendors, we do support them with our designs, specifically with the open source designs we do of our library. So our IP core library is called grlib, and we offer, almost like 80% of everything we develop, we put in open source under GPL license that developer can download evaluate that, and that's great. I mean, it is a very good way of see what you buy in the end, but also for academia, they can work freely on those IP cores, which also gives additional insight in what we are doing.
Thanks to Sandi, Habinc, General Manager at Frontgrade Gaisler, for those insights into the IP that makes space exploration happen. If you're interested in hardened processor IP for harsh environments, you'll be able to catch up with the Frontgrade Gaisler team at the HiPEAC conference, which takes place in Munich from the 17th to the 19th of January 2024. To learn more, drop by the website hipeac.net/conference for further information.